Delaware Tech, Chem 100, Chem 110, Unit 2 continued, energy. What is energy? Well, energy is the ability to do work or to heat an object. So you can either do work on an object by moving that object, for instance, or heating it up. And physicists like to look at the first definition of energy, the ability to do work. Chemists tend to look at the second definition of energy, heating up an object or cooling down an object. That's the transfer of energy. So let's talk about the types of energy. Work is one type of energy. So this is the energy needed to move an object or to change an object. If I move a desk from one part of the room to another, I've imparted work on that object. If I've crumbled up a piece of paper, I've changed the object by putting work energy into that object. But there are many types of energy, and all forms of these energies can be interconverted into one another. Not always with perfect efficiency, but they can all be turned into one another in theory. So let's talk about some types. Work, as I already mentioned, energy needed to apply a force to move an object. Heat energy, also known as thermal energy, we abbreviate it as Q or H. This is the energy transferred from a hotter object to a cooler object. This even includes heat from friction when we're moving something, say, on the floor and it's sliding along and warming up. That would be heat energy or thermal energy. And heat energy is always transferred from the hotter object or area to the colder object or area. In reality, while we have a such thing as heat, there really is no such thing as quote-unquote cold. Cold is merely the absence of the heat. We also have other ways of looking at energy, and these are not mutually exclusive from the other categories, but we can also divide up energy into two different categories: potential energy, abbreviated PE or sometimes U when you're taking thermodynamics courses or physics courses, and kinetic energy, abbreviated KE or E sub K. Now, the difference between these two, kinetic energy, I'll start with first, is the energy resulting from movement. So if an object is moving, it has kinetic energy. Anything moving has kinetic energy. If it's not moving and the energy is stored, just stored in that object in one way or another. So, for instance, gasoline in your gas tank. It's not moving anywhere. You haven't even turned on the car, but there's energy stored in the chemicals of that gas. If you have a spring compressed very tightly and you let it go, it's going to release energy. So while it's still compressed, it is stored in there. If you're holding an object above a cliff and you haven't let the rock go that you're about to drop, there is energy stored in the fact that it is sitting very high above the ground, and therefore gravity was going to pull it the second you let it go. Those are forms of potential energy. They have the potential to be turned into movement or kinetic energy, so that would be called potential energy. We have other ways of distinguishing energy types. We have chemical energy and nuclear energy. Chemical energy refers to energy that's released or absorbed in a normal chemical reaction. And we'll talk about chemical reactions when we get to Unit 5. But chemical reactions are reactions where we're adding a couple chemicals together and we make new chemicals, and heat is either produced in the reaction and so it will feel hot, or it's absorbed in the reaction and it will feel cold. Those are normal chemical reactions. But we also have what are called nuclear reactions, where we're actually changing the atoms themselves. In chemical reactions, we don't change the atoms. We change what the atoms are attached to, the bonds between the atoms. That happens in every chemical reaction. But in nuclear reactions, we're actually changing the identity of the atoms. So we might be changing hydrogen atoms into helium atoms, or uranium atoms into barium atoms. So completely different elements are being produced because you're changing the nucleus of the atoms, the center of the atom itself. And there's a lot of energy produced from those. We also have electrical energy, and this could be either in the form of potential energy. If we just hold charges away from each other, we don't let them go, that's potential energy. And of course, when we let them go and they start flying towards or away from each other, that would be kinetic energy. Radiant energy. Now this one is important to everyday life. Radiant energy is the electromagnetic energy, for instance, from the sun. So it's basically all the different types of light that are formed in nature, and in our world that tends to be originally from the sun's energy. So let's look at some of those types. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all different types of light, technically, and because they are all part of the electromagnetic spectrum of energy, and that's shown here. So you can see the low energy forms of electromagnetic radiation are on the left, like radio waves, and the very high energy ones, the ones that are quite dangerous, are on the right, like high-energy ultraviolet rays, X-rays, and gamma rays. These can do severe damage to living organisms. And in the middle, we have microwaves and infrared and visible and lower ultraviolet. And you'll notice the visible wavelengths, the visible range of the entire light spectrum, the entire electromagnetic spectrum, is an incredibly thin, tiny little strip of frequencies and wavelengths and energies. Our eyes have evolved to basically only pick up that tiny range here that's labeled visible. We don't see infrared, we don't see ultraviolet. And just a little point here, you'll notice the visible wavelengths are made of the rainbow of colors. The rainbow of colors, we name them with 7 different colors, but in fact there are literally infinite numbers of colors in the visible range. But you'll notice on the left side of the rainbow it's red, and on the right side of this rainbow it's violet. Well, anything lower than red is infrared, lower than red. And anything greater than violet in the visible spectrum is ultraviolet, greater than violet, way past violet. And that's where those words come from. You've probably been using them all your life and didn't realize that they refer to the colors red and violet of the rainbow. One's on the left side of the rainbow and one's on the right side of the rainbow. All right, so we have all these different energy forms, different potential energies, different kinetic energies, and some of these others in here are also potential and kinetic energies, so they're not mutually exclusive. You can have work energy, you can have heat energy, you can have heat energy from nuclear reactions or chemical reactions, you can have radiant energy from the electromagnetic spectrum here on the left, but all of them can be converted to any other one. So you can convert potential energy from holding an object high above the ground, for instance, and turn it into work. You imagine if you dropped a rock on a seesaw, and it would hit the seesaw, and the other end would spring up and move something. That would be work. As the object is dropping, it's turning its potential energy into kinetic energy. It starts moving faster and faster. And right before it hits the ground, it has a lot of kinetic energy and almost no potential energy because it's just barely off the ground. So that would be a way of converting potential to kinetic. Shooting a rocket up into the air. If you shoot it up high enough with enough kinetic energy, it'll reach a point where it will stop moving, so there's no kinetic energy, and then right before it starts falling, it's very high above the ground. Well, that's potential energy, and that gets converted back into kinetic as it crashes down to the ground. Well, when it hits the ground, then it doesn't have any potential energy, and it doesn't have any kinetic energy. So where did the energy go? Well, it went into the ground, and it probably went into the ground doing one of two things, either heating up the ground or deforming the ground, making a hole in the ground, and that would be a form of work. It might even cause an explosion. That would be a chemical heat reaction. So if you trace back any energy that you use in everyday life, you can really get back to some form of nuclear energy. And while you're not responsible for this, I want to show you the pathway. So if you're running, for instance, you've got kinetic energy. You're moving along. Where did you get that energy? Well, you got it from eating the hamburger you had earlier that day. And that's chemical potential energy that was stored in your food. Well, where did the hamburger get it? Well, the hamburger used to be a cow, and the cow got it from eating grass, because the grass had in it kinetic potential energy that was stored in the chemicals in the grass. Well, where did the grass get it? Well, the grass got it by photosynthesizing using the light from the sun to produce the sugars and other substances in the grass. So it used light. And H nu, that's the Greek letter nu, it's not the letter V. H nu is the symbol for light or electromagnetic radiation to a physicist. You don't need to know that for this course. But it's turned into potential energy of the food source. Well, where did the sun get it from? Well, the sun got it by fusing hydrogen. So here's another use of the word fusion that I mentioned earlier. It takes 4 atoms of hydrogen and crushes them together because of the gravity of the sun, literally squeezes the atoms together to form 1 atom of helium. And that's a nuclear reaction. That's called a fusion reaction. You're not responsible for that in Chem 100. You will be responsible in Chem 110 for that. And so that's fusion. So where did the sun get its energy from? Well, it got it from something called the strong nuclear force, which allows these atoms to be crushed together and form a new nucleus to that new atom. And that's way beyond the scope of this course. Another example, you warm your house. Where do you get the energy? Well, you get it from the electric heater or whatever appliance is used to warm the house. Where did the electricity come from? Well, it came from the power plant that burned oil or coal or natural gas. Where did the natural gas get it from? Well, or the oil or the coal. Well, they used to be living organisms millions of years ago, and they got it from the sun eventually, and we all know the rest of that story. Eventually, you get back to this strong nuclear force that brings particles, the nuclei, the centers of atoms together under certain conditions. So it all connects to one another. Now, we have a couple laws of conservation. There's the law of conservation of energy. And this is that states that energy cannot be created or destroyed in ordinary reactions or changes. In other words, I can't get rid of the energy. I can turn it in from one form into another, sometimes easily, sometimes not so easily, but it's always the same amount of total energy, as long as I'm doing a chemical reaction or some kind of physical change. You'll notice the thing I didn't include here was nuclear reactions, and those are special cases. So it can only go from one form of energy to another. If you remember that wheel of different energy forms, different forms can be converted to other forms. The exception is the nuclear reaction. In nuclear reactions, you can get some energy turned into matter, and you can get some matter turned into energy. More of the second one. More times you'll see matter turned into energy. Now, we also have a rule, conservation of matter or conservation of mass. People use both terms. In this rule, mass cannot be destroyed. So just like energy can't be destroyed in normal reactions, chemical or physical reactions, mass can't be destroyed. If you start with a certain number of atoms in a chemical reaction, you'll end up with the same number of the same atoms at the end of the reaction. But again, you'll notice I did not include nuclear reactions, in which case you can turn some atoms into other atoms, and you can turn some matter, some parts of the atoms, into pure energy. So we have this overlying rule that combines the two, and that's because of this little boy here on the right. That's his sister on the left. You probably don't recognize this little boy. This is what he looked like when he grew up. This is Albert Einstein, and Albert Einstein worked out the formula of E equals mc squared, or energy equals mass, times a conversion factor, which happens to be the speed of light squared, or c squared. C is the abbreviation for the speed of light. A very, very large number because speed of light is incredibly fast. Remember, it's that almost 300 million meters in a second. So when you take a small amount of mass and you multiply it by the speed of light squared, so you're multiplying it by a very large number times itself, another very large number, even a small amount of mass will be turned into an enormous amount of matter, of energy in the process. And this tells us a couple things. Number one, if we're able to turn matter into energy, we can get gigantic amounts of energy from even small amounts of matter. Number one. And number two, to a physicist, this is telling them that, hey, matter and energy are actually really the same stuff of the universe. They're just different forms. And so while we frequently distinguish between matter and energy, in reality, to a physicist, they're really the same thing. So when you look at all the matter and all the energy in any kind of reaction, whether it's physical or chemical or even nuclear, you don't lose anything ever. The total amount of matter and energy together will be the same amount before and after any kind of reaction. But it also means that you only need a little bit of matter to make a lot of energy. So if you took 1 gram of matter, 1 gram, we're talking about 1 paper clip or 1 raisin, that's about a gram, and you turned it into energy, this would produce this number of joules of energy. Now, we haven't talked about the unit joule. Joule is about a fourth, joule is about a fourth of a, a 4,000th of a calorie that you know of in relation to food, what we call the big C calories. So this is a large number of these small joules. So if you're asking, well, I don't know what that means, how much energy is that? 1 gram of mass, if it was turned into pure energy, this is enough energy to light a 100-watt light bulb for 30,000 years. So this is why people are so interested in nuclear power, because you get an enormous bang for the buck, no pun intended. It doesn't take much matter to be turned into energy to produce all the energy human beings could ever need if we had a way to do this. So this is why people are interested in developing more and more advanced methods of nuclear power. So we combine the mass conservation law with the energy conservation law, and we have what's properly called the law of conservation of mass energy. The total of the mass and the energy will remain the same for any kind of change. So let's look at potential versus kinetic. Remember, kinetic is movement, potential is stored. Is it potential, kinetic, both, or neither? Well, we have about to ski, skiing, and just before stopping. Well, if you're about to ski, you have potential energy. You're at the top of the mountain, you haven't started moving, the energy is stored in the fact that you're high up and gravity is pulling you down. While you're skiing, you have both. You're moving and you haven't hit the bottom yet, so you still have some potential and you have some kinetic. Just before stopping, you're moving as fast as you're probably going to move, so you have kinetic, and almost all your potential is gone, so it's pretty much all kinetic at that point. Let's look at 3 more. Falling, sitting, and running. Well, if you're falling, well, you haven't fallen all the way. You're clearly moving as you're falling, and you're still going to fall more, so you have both kinetic and potential. Sitting, you're above the ground. You're not sitting on the ground. You're probably, well, in this case, we're talking about sitting on a chair. You're sitting on a chair. You have potential energy. You have the potential to fall a little bit further to the ground. Running, you have a little bit of both. You're moving already, and you could fall all the way down to the ground. A spring, a compressed spring, a stretched spring. Well, people look at a spring and they go, oh, that's potential energy. No, the spring by itself, if it's not compressed or it's not stretched, doesn't have anything. There's no energy stored in it until you compress it or you stretch it. Then it's potential energy. Because once you let go of it, it will move. A stretched spring will spring down to being smaller, and a compressed spring will stretch back to being larger. Climbing. Climbing, you're moving and you're above the ground, so that's both. And a chemical bond. Now, this is the trickiest one of the bunch, and we talk about the potential energy in a chemical bond, but we really do not mean that. What we actually mean is the potential energy that is released as a result of breaking some bonds and potentially making new bonds that are better, that are more stable. And if you make bonds that are more stable means less energy, so that energy has to go somewhere, and that energy goes into becoming heat. So if you start with unstable chemicals, high energy chemicals, and you go to very stable chemicals, low energy chemicals, and if you have trouble remembering it, think about unstable individuals. They're very high energy, and stable individuals are quiet and sedate and low energy, right? So high energy becoming low energy, well, energy can't be lost. Remember, it has to go somewhere. Well, it goes, in this case, in the form of heat, and you release an enormous amount of heat. This is methane. CH4 is the chemical structure for methane. Methane is the major component in natural gas. The vast majority of natural gas is methane. And when you burn it with 2 molecules of oxygen, you make 1 molecule of carbon dioxide and 2 molecules of water. Oxygen gas is not a very stable molecule, and you have 2 of these unstable molecules with terrible bonds, and you're making carbon dioxide with excellent strong bonds and waters with excellent strong bonds, and as a result, you're going from high energy methane and oxygen to low energy stable carbon dioxide and water, and that releases an enormous amount of heat, almost 800,000 joules for every one of these chemical reactions. What we call a mole of methane, and we'll talk about moles later. So this is the release of a chemical energy. It's not in any particular bond. It's when you look at all the bonds that are broken and all the bonds that are made. And we'll stop here and start with heat next time.